Welcome to lesson 5.4. So last time we talked about the first part of the fundamental theorem of calculus. Today we will talk about the second part of the fundamental theorem of calculus. So let's get cooking with this second part of the theorem. So basically the second part of the theorem, so the first part of the theorem said to evaluate a definite integral, then you find the antiderivative and you plug in the upper bound, plug in the lower bound and find the difference. So it makes sense that if integrals are defined by antiderivatives of a function, then the derivative of an integral would give me the function. So basically what this is saying here is if f of x is continuous and on this closed interval and g of x is equal to the integral from a to x of f of t dt, then if it is continuous on that closed interval and is differentiable on the open interval, then the derivative of this integral would be equal to f of x. So let me show you kind of how this works. So basically, if I take the derivative of an integral, and this is an important part right here. If I take the derivative of an integral where the lower bound is a constant and the upper bound is x or whatever variable I'm differentiating with respect to, then the derivative of the integral is equal to the function. And let me show you how this kind of works right here. So if I'm taking the derivative of this integral right here, so the integral, the antiderivative, if I say that the antiderivative is big F of t, and I evaluate that from a to x, then what I'm doing is I'm taking the derivative of the difference between these two things. So this is going to be f of x minus f of a. So remember from our derivative rules, if we're differentiating this expression right here, I can differentiate each part individually. And this is why it's key that this lower bound is a constant. When I take the derivative of these two quantities right here, this one is a constant and the derivative of a constant is 0. So then this would be the derivative of the antiderivative in terms of x, which means that this would just be f of x. So this is just an explanation of how this fundamental theorem of calculus part 2 works. So again, key here is that the lower bound is a constant and that the upper bound is the variable that I'm differentiating with respect to. So let's take a look at an example. So if g of x is equal to this integral from -4 to x of e to the 2t cosine squared 1 minus 5t dt, if I'm differentiating g of x, I just look at this and say, okay, well, this second part of the fundamental theorem of calculus applies because the lower bound is a constant, the upper bound is x, which that's what I'm differentiating with respect to. So then g prime of x would just be e to the 2x cosine squared 1 minus 5x. And that would be the derivative. It's that simple if it's set up in the way such that the second part of the fundamental theorem of calculus applies. So let's take a look at one that is not exactly like that. So with this one, there are a couple things that I see. Number one is that this time x is in the lower bound. So one thing that I could do to fix that part of it is I could say f of x equal to negative integral from 1 to x squared of t to the 4th plus 1 over t squared plus 1 dt. So now at least I have x in the upper bound. So what I could do is if I'm trying to differentiate with respect to x, I'd notice that this is x squared up here. So I'm going to show you this long explanation first, and then I'm going to give you the notation for the long explanation, then I'm going to give you my shortened version of what's going to happen. So what we could do here is we could let u equal x squared. So if we let u equal x squared and u is a function of x, we're going to redefine this as u of x equals x squared. What I could do is I could then say that f of x is equal to the integral, well, negative integral from 1 to u of t to the 4th plus 1 over t squared plus 1 dt. So then when I take the derivative, f prime of x would be equal to, right here, I could write this in terms of u. So this would be negative u to the 4th plus 1 over u squared plus 1. And then what I would also have to keep in mind is if this is in terms of u and u is a function of x, then I would also have to multiply this by the derivative of u, which the derivative of u would be 2x. So then what this would look like, this would be negative 2x times, if u is equal to x squared, then this would be x to the 8th plus 1 over x to the 4th plus 1. So this is the notation of how this works. Basically what I'm doing is I'm substituting in a variable for the upper bound. When I differentiate, then I have to apply the chain rule, and I differentiate this function first and then multiply by the derivative of u, which gives me my final answer. So this is the notation of what this looks like, and we could actually extend this if both the upper and lower bounds were in terms of some other variable. But the basic idea here is if your upper bound is a function of x, then I substitute in that function of x and then multiply by the derivative of that function. If your lower bound is a function of x, I substitute in that lower bound, then multiply by the derivative of that, and then make it negative to account for the fact that if I wanted to apply the fundamental theorem of calculus here, I need to switch the bounds. So let me show you an example of what that looks like. So here I have a function where the upper and lower bound are in terms of x, but they're both functions in terms of x. So what I could do is I could plug the upper bound into the function. So this would be 3x squared times sine of 1 plus 3x squared. And then I multiply by the derivative of 3x. So then this whole thing will be times 3. All right, so I plugged in the upper bound, multiply by the derivative of the upper bound. And then I subtract, because again, lower bound, I'm gonna have to subtract, but I'm gonna subtract, I'm gonna plug in the lower bound, so this would be square root of x squared times sine of 1 plus square root of x squared. And then I'm gonna multiply by the derivative of the lower bound. So this would be 1/2 x to the negative 1/2. And then this would be the derivative. Because this upper and lower bound are both in terms of x, I substitute them into the function and then multiply by the derivative because I'm going to have to apply the chain rule when taking the derivative. And then you can simplify this. I'm going to leave that simplification up to you, but you could simplify that to make it appear in a much nicer, cleaner form. So that is it for today. Today we talked about the fundamental theorem of calculus, part 2. I don't know why I got these backwards in both videos. This was part 2. And then we also talked about applying the chain rule to the second part of the fundamental theorem of calculus, if necessary, if my upper and lower bounds are in terms of x. So I hope you took some good notes. Hope you come to class with some questions and ready to learn. And I hope you have a fantastic day. I'll see you in the next video.